Hi guys, another video on vectors. So welcome to 6.4, vectors and dot products. Alright, let's see how many interruptions we can get today. Okay, so for those of us who are unfamiliar with this, I know a lot of you probably saw it in your physics class, but a dot product of two vectors, u and v, it's written like this, u dot v. We don't say u times, it's u dot. You do u sub 1 times v sub 1. Plus u sub 2 times v sub 2. This gives you a scalar, not a vector. Just keep that in mind. So some properties of the dot product, you can check it out in your book. The proofs are also there. I'm only going to do one proof with you today. Later, thought I'd spare you that, trying to focus on what's important here. But you have the commutative property here. U dot v is the same as v dot u. The 0 vector dotted with any other vector is just the scalar 0. Here you have the distributive property, u dot, the addition of two vectors v plus w. That would be u dot v plus u dot w. Over here, number 4, if you dot a vector with itself, v dot v, that's really the magnitude squared of that vector. And then for number 5, if you had c, which is some scalar, times the quantity u dot v, again, you can think of that as c times u dotted with v, or u dotted with c times v. Properties that you're all familiar with, just a little bit different. All right, so let's look at the first example. Let u be the vector 2, 6, v be negative 1, 5, and w be the vector negative 3, 1. Find u dot v. Okay, so we are literally just going to do 2 times negative 1 is negative 2, and then I'm going to add to that 6 times 5, which is 30. So 30 minus 2, that's a really weird 2, 28. That's your answer. For part B, if we did u dotted with v plus w, so if you want it, there's a couple different ways you can go about doing this, but the way I'm going to show it is thinking about it as u dot v plus u dot w. So u dotted with v, I already have that answer from above, that's 28. And then u dotted with w, so that's going to be 2 times negative 3, that's going to be negative 6. And then negative 6 plus 6 times 1, which is 6, that's 0. So I get 28 again. So that's our dot product, number 1. Okay, let's move on to the next definition, not to waste your time here. So the angle between two non-zero vectors is the angle theta, and theta has to be between 0 and pi inclusive, between their respective standard position vectors. So it looks something like that there for you. Okay, so this angle can be found by using the equation cosine of theta equals u dot v divided by the magnitude of u times the magnitude of v. To come in handy later, if you solve this equation, you could solve the equation right for u dot v. You would have this here. I know you can do that, or algebra there. So this is a proof that I'm going to run through with you quickly. Don't fast forward, just bear through it with me. All right, so by the law of cosines, this picture here might help you here. So if you had vector u and vector v and angle theta, then this vector here would be v minus u. So by the law of cosines, referring to this image right here, the magnitude of v minus u quantity squared would be equal to the magnitude of vector u squared plus the magnitude of vector v squared minus 2 magnitude of u times magnitude of v cosine of theta. So that is just taking your law of cosines and substituting in your vector magnitudes. All right, so I'm not going to repeat the right-hand side. I won't put you through that, but that's staying the same the whole way through to here. So one way you can think about this, we said back here on your properties, if we dot a vector with itself, that's really the magnitude squared of that vector. So if I have the magnitude of v minus u squared, that's really v minus u dotted with v minus u. So really this is v dot v minus 2 v dot u plus u dot u. Think about foiling. Okay, the right-hand side is staying the same. So really, v dot v, again, by definition, that's the magnitude of v squared. U dot u is the magnitude of u squared. So now, again, looking on what you have, you might be like, well, you always told us to keep the right-hand side or the left-hand side all the way to the end. Well, we're actually deriving an equation. We're not proving that one side equals another. We're deriving a formula here. So just keep that in mind. So at any rate, your two magnitudes cancel out. Okay, that's why you see those crossed out there. And I'm trying to, again, prove to you this equation. Where does the cosine of theta come from? So I would divide both sides by the -2 magnitude of u, magnitude of v to get this here. Your -2's cross out. You're left with u dot v divided by magnitude of u, magnitude of v, which is what I was trying to show you to begin with. So just a little, had to do one proof, guys. All right. So let's take what we just learned and apply it to an example. So number 2, find the angle between u is -2,3 and v is 1, -5. So sorry, sometimes when I'm doing the notes, I just get so involved with doing the problem. I'm like, oh wait, I was going to do that on the video. And this is one of those cases, so I decided to leave it. But so here we are. All right, so I am substituting in to our cosine of theta equation, but notice that I solved for theta already, so I took the cosine inverse, again using this equation here. So I had to do u dot v. So this is u dot v divided by the magnitude of u. So the magnitude of u, so that, how did I get 4? So that's -2 quantity squared plus 3 squared, which is 9. And then I don't know why over here I decided to write 26, but 1 squared plus quantity 5 squared, that's going to be 26. So 13 times 26, that gives us the radical 338. Up here, when we dot those two vectors, take the dot product of those two vectors, you're going to have a -2 and a -15, so that's where the -17 comes from. You're going to use your calculator to take the cosine inverse, and you will get 157.62 degrees. Just make sure that you're in degrees. Another way to look at this one is graphically. And just to show you, I know this is just drawn magnificently. So here's vector u. It's at -2, 3, and vector v is at 1, -5. And so if you were to go through and actually find the angles for each vector, so to find theta here, right, remember you're taking the inverse tan of 3/2, 3 over -2. Excuse me, Aiden. Okay. So when you do that, don't write on that, you get -56.31. And so how do I find that angle? I'm going to take 180 and subtract that 56.31. So this angle right here is 123.69. Now to find the angle for v, I take the tan inverse of -5 over 1. So when I do that, you get -78.69. So how do I figure out what that angle is? We are going to take, 360 and subtract that 78.69. Those are degrees. And so that gives you 281.31 degrees. You're like, well, how the heck do we get 157? So remember, the definition of that theta is the angle between two non-zero vectors. It's between 0 and pi inclusive, between their respective standard position vectors. So if I take 281.31 degrees and subtract 123.69 degrees, that gives you the 157.62 degrees. I was making sure the decimal was off. I'm done. 69. Yep. It's just a visual for you to think about it that way. Okay. So, I have a visitor while we are filming up here. No, please just play. All right. So, next topic. Since we know that the cosine of 90 degrees is 0, two vectors are called orthogonal if u dot v is 0. This means that the 0 vector is orthogonal to every vector because the 0 vector dotted with u equals the number 0, which means they meet at a right angle. So number 3, are the two vectors u equals -4, 2 and v equals 1, 2 orthogonal? So how would you check it? Well, you're going to find the dot product of those two. And so -4 times 1 gives you -4. And 2 times 2 is 4. So do I get 0? Yes, I do. So are they orthogonal? Yes, they are, because you get 0 from doing that. All right. So here we go. Again, people probably did this in physics, so hopefully that's helping you. And if you have your own way of doing this, go for it. We're getting into some more complicated stuff here. So finding vector components. Here I am with my notes. We now do the reverse of adding two vectors to find their resultant. We decompose a vector into the sum of vector components. So if u is a non-zero vector such that u equals w sub 1 plus w sub 2, where w sub 1 and w sub 2 are orthogonal, sorry about this, and w sub 1 is parallel to v, which means it's a scalar multiple, then w sub 1 and w sub 2 are called the vector components of u. If you're like, what is she talking about? Here we go. I have a lot of different ways of showing this to you. So that vector w sub 1, another name we need to familiarize you with, is the projection of u onto v, and it is denoted like this. W sub 1 equals the projection of u onto v, where v is a subscript. In the equation that we use here, we say the projection of u onto v is equal to u dot v divided by the magnitude of v squared times the vector v. W sub 2 is defined as vector u minus w sub 1. So here are some visuals about what is going on here, and we're going to do some problems together. Well, I guess just me talking to myself, but all right, so if theta is acute, all right, here is your u, and here are the two pieces, the two vectors that make up u that are orthogonal. Remember, that means they meet at a right angle. So here's w sub 1, and here's w sub 2. This is 90, so therefore this is 90. There's just a lot going on, so I don't want to write the 90 there. Okay, here is this vector v and the angle theta. All right, w sub 1, like it says up here, is the projection of u onto v. All right, another way to think of this is w sub 1 is kind of like the shadow of, I know that's so weird, of u onto v in the direction of v. All right, so again, u is made up of two parts, w sub 1 plus w sub 2. These are called the vector components, and w sub 1 and w sub 2 are orthogonal. Another big thing like I just mentioned, but I rewrote it here for you. W sub 1 is parallel to v. Right here you can see it very nicely, which means that w sub 1 is some scalar times v. All right? Just the other situation to look at here, if theta was obtuse. So again, here is, come on and focus. So here is your u. Here's your w sub 2 and your w sub 1. And again, they meet at, w sub 2 and w sub 1 are orthogonal. They meet at a right angle. Here's your theta, and this is a little bit different, but here is your v. Okay, the vector v. All right, so we are going to, oh, I lied. I have one more proof. Okay. So just the proof to show you where the projection equation comes from. So we know that u equals w sub 1 plus w sub 2. And we also know that w sub 1 is a scalar multiple of v. So for w sub 1, I can rewrite that as c times v. So again, I'm manipulating both sides because I'm trying to show you where an equation is coming from. So I'm going to take the dot product of each side with v. So this was the next step. So nothing on the left has changed. So kind of distributing in there, you got CV dotted with V plus W sub 2 dotted with V. By definition, V dot V is the magnitude of V squared. Okay, and we also know that W sub 2 and V are orthogonal. Let me show you some of those visuals again. Okay, so W sub 2 and V, W sub 2 and V, they are orthogonal. So that means they meet at a 90-degree angle. Whoops, sorry. So therefore their dot product is 0. So solving for this scalar C, we get U dot V divided by the magnitude of V squared. We know that W sub 1 is defined as, the projection of U onto V, which this thing would focus. We also talked about previously that W sub 1 is a scalar times V. It's a scalar of V. So taking what we found for C and substituting it in, I can throw some parentheses in there, it's your C times your vector V. I just wrote to check out the webpage because I did post that along with the assignment today, and I also created a new tab called Helpful Links or something to that effect, which gives you a really good visual of projections and vectors here. So I usually show that when we're in the classroom, but if you want to check that out, the link was posted there. All right, let's keep going to see how long I can go before I'm going to be interrupted. All right, so number 4, find the projection of vector U, which is 5, 2, and vector V, which is 3, negative 1. So first thing, find the projection. Then I want you to write U as the sum of 2 orthogonal vectors, one of them, which is the projection of U onto V. All right, so here we go. First, let's find the projection. So remember, the projection is really just talking about W sub 1. So W sub 1 is equal to the projection of U onto V. All right, and following our equation that we have here, let's go back. Oh gosh, I have to, my notes are all off now. La la la. No, it's probably, it's up here. So it says to take the dot product, come on and focus, of U dot V and divide by the magnitude of V squared and multiply by the vector of V. All right, so U dot V. So 5 times 3 is 15, and then 2 times negative 1 is negative 2, so that's going to be 13. And then the magnitude of V squared. So that's going to be root 9 plus 1, which is root 10, and then I square root 10, which is 10. And then I have to multiply it by vector V, so 3, negative 1. So that ends up giving me, so let's see, distribute in that 13 tenths. So you're going to get 39 over 10, comma, negative 13 over 10. Okay, so that's the answer to find the projection. All right, second thing, then write U as the summation of 2 orthogonal vectors. All right, so, well, I know that U is equal to W sub 1 plus W sub 2, and it says one of which is the projection of U. Well, hey, guess what? Projection of U onto V, that's W sub 1. So I already have W sub 1. So I have to find W sub 2. So W sub 2 is U minus W sub 1. So that just means I'm taking 5, 2, and I'm subtracting that W sub 1 I just found. So 39 tenths and then negative 13 tenths. And so after some fancy arithmetic, I'll spare you the details, you should get 11 tenths and 33 tenths. So again, that's your W sub 2. So to answer that final question, I just asked you to write U as the summation of 2 orthogonal vectors, like we just said, is W sub 1 and W sub 2. So W sub 1, I'm just going to write that as is, 39 over 10, comma, negative 13 over 10. And then I'm adding W sub 2 to it, which I just found, 11 over 10 and 33 over 10. So that's kind of the answer to part B, and this was the answer to part A, just to summarize that for you. Okay, now we get back into force. So in the 6-3 video, I mentioned force, and I mentioned the projection a little bit, but I don't believe many of you conquered the problems that way, so we're going to look back at this a little bit more in depth here. So force, we have to talk about force and work, I know. So force F due to gravity pulls objects down, and usually it's ramps, but most of the problems we're looking at is ramps, but not necessarily, and against a ramp. Force can be thought of as W sub 1 plus W sub 2. All right. So here's your visual. Here's the object on some ramp. You have W sub 2, W sub 1, and then the force of that object. W sub 1 right here, that's the force needed to keep the object from rolling down the ramp. W sub 2, that's the force the object must withstand against the ramp. Remember, W sub 1 and W sub 2 are orthogonal, so they meet at a 90-degree angle. So with that information, again, if you have your own ways that you learned how to do this in physics, go for it, but I will explain it the way that we explain it in pre-calc. So, number 5, again, this is similar to the one we did the other day in 6.3. You have a 500-pound piano, sits on a ramp that is inclined at 45 degrees. What force is required to keep the piano from rolling down the ramp? All right, so here is my beautiful piano. It says the ramp is inclined at 45 degrees. There's multiple ways to draw this one. Over here, let me just go back, right? If this is W sub 2, we know that this would also have the same length or same magnitude as W sub 2. If this is W sub 1, same thing down here. That's the same magnitude as W sub 1. So I just drew this a little bit differently. So W sub 1, again, that's the force needed to keep that piano from rolling down the ramp. And W sub 2 is the force that the piano has to withstand against the ramp. And here's your force. So we are asking what force is required to keep this thing from rolling down the ramp. So that's your that's V, we can call it. Again, what do you have to push against that piano to keep it from rolling down? So the force due to gravity, most of you might be able to just look at this and say, okay, it's it's a unit vector directly downward, and it's going to be negative 500J. For people who don't understand that, well, let's look at that. So it's a 500-pound piano, and if I thought of it as right here, right, the magnitude of this vector is going to be 500, and it's going downwards. So I can write this as negative 500J. I could also rewrite it as 0, negative 500 in component form, if that makes more sense to you. So what we need to do is project that vector F onto unit vector V in direction of the ramp to say, hey, what force do you have to apply to keep this thing from rolling down the ramp? So to begin, we need to figure out, well, what is vector V? Okay, so if you go back to last section, remember we said it's a unit vector. And so the angle there is 45 degrees. So really we're looking at the cosine of 45 degrees I plus the sine of 45 degrees J. So another way to think of that once you evaluate it, in component form, that would be root 2 over 2, root 2 over 2. So there's our vector V. Okay, remember, we need to project F onto vector V. So really I have to figure out, well, what's going on with W sub 1? Because whatever the magnitude of that vector is, that's what I'm going to have to apply to keep it from rolling down the ramp. So W sub 1, by what we've been talking about by definition, is the projection of F onto V. And so by our equation that we proved, I would take F dot V, divide by the magnitude of V squared, and multiply by V. So F dot V, that's going to be 0 times root 2 over 2 is just 0. And then when I do negative 500 times root 2 over 2, that's going to be negative 250 root 2 divided by 1. Again, this is a unit vector, so the magnitude's 1, but if you need to do it out, you can do it out. And then we multiply by V. So root 2 over 2, root 2 over 2. Once again, I left myself a ton of space here. I'm kidding. All right, so, I mean, really what's going on here, this is just negative 200. If you want to distribute in, but I'm going to leave it like this to kind of prove a point or show a point. I'm not really proving anything. So this is, the magnitude of W sub 1. So they asked what force is required to keep the piano from rolling down the ramp. So basically what has to be pushed against it from rolling down the ramp. So we're looking for the opposite of this value of the magnitude, which is going to be 250 root 2. And if you want to throw that in your calculator, you can, but that is the force that we need to keep it from rolling down the ramp. Again, if you have a better way that you like to do this, that's perfectly fine. All right, so there's force. Moving on to work. 2 more. Bear with me here. So work. Work W is done by a constant force F as its point of application moves along a vector. PQ is given by either of the following. So if you're moving an object from P to Q, and that force is parallel to the path that the object is taking. So again, force acts along the line of motion. Work is the magnitude of the force times the distance. So magnitude of the force in this case, well, that's just magnitude of the force. And the distance, that would be the magnitude of PQ. You can also think of that as the projection of F onto PQ, dotted with your magnitude of PQ. The other situation that you might have is that you are moving an object from P to Q, but the force, like a rope, you're pulling up on a rope. Okay, that's an example there. For F with some theta. So again, you have the projection of F onto PQ times the magnitude of PQ. All right, another way to think about this, you could really think of both of them like this. Thinking of this as a right triangle, we know that the cosine of this theta would be the magnitude of the projection of F divided by the magnitude of F. All right, so therefore the projection of F onto PQ would be cosine of theta times the magnitude of F, which is just F times dotted with, P, the vector PQ. So you're like, oh my gosh. All right, maybe you're not. Maybe you've seen this before. We're going to do 2 of these examples with work, and then I probably bored you enough here. All right, so number 6, a man pushes a broom with a constant force of 40 pounds. The handle of the broom is at an angle of 30 degrees. How much work is done pushing the broom 30 feet? Okay, so here's your 30 degrees. All right, this is a situation where you're going to move the broom. What are we moving? Yeah, we're going to push the broom 30 feet. And it's at some sort of an angle. It's not exactly parallel to the line of motion there. So first we have to figure out, well, what's F in terms of the vector form. Okay, so I know the magnitude of F is 40 because it says 40 pounds. And then my angle here is 30 degrees. So 40 cosine of 30 degrees, sine of 30 degrees. And so, I mean, I can distribute that in and just write it as 40. I mean, you can also evaluate it. Whoops, 40 sine of 30 degrees. Okay, so now also this vector right here, all right, your PQ, we'll call it. How would I write that in component form if this thing would not be blurry? That we can think of that as 30, 0, because we're moving it horizontally. So for our work equation, we take F and we dot it with PQ. So I didn't leave myself much room, but so we're taking, come on and focus. So we're taking F and dotting it with PQ. So this is where you can use your calculator. You're going to do 40 cosine of 30 degrees times 30 plus 0 times this 40 sine of 30, which is just 0. So you should get 103.9, and this is called foot-pounds for that answer. So usually the math isn't difficult. It's usually the setup and understanding the problem. All right, last one about a sliding door. So to close a sliding door, kind of similar to something maybe on a barn or a garage, you pull a rope with a constant force of 50 pounds at a constant angle of 60 degrees. Find the work done in moving the door 12 feet to the closed position. So here's my beautiful barn door. You're going to pull it with a rope so that it slides across into place from P to Q. The distance from P to Q is 12 feet. It tells you that the angle is pulled at a constant angle, of 60 degrees, and that your force is 50 pounds. Okay, so, thank you. All right, so we want to know how much work is done. All right, well, let's first figure out what F is. So our magnitude here is 50, and my angle is 60. So it's 50 cosine of 60, 50 sine of 60 degrees. Okay. And so let's figure out what work is. So work, another way we can think about it is just F dotted with PQ. PQ I can think of as 12, 0, again, because we're moving it horizontally. So work, we can take 50 cosine of 60 degrees, 50 sine of 60 degrees, and dot that with 12, 0. And so when we do this, let's just, am I in the right? Yeah, I'm in the right setting. Okay. And when you do that out in your calculator, again, the dot product, the zeros are going to cancel. So really all I care about is 50 cosine of 60 times the 12. That's going to give you 300 foot-pounds. Another way you could think about this one is you could do the cosine of 60 degrees times what's your magnitude of F, 50, times your magnitude of PQ, which is 12. And if you do that out, you'll get the same answer of 300 foot-pounds. All right, good luck, guys.